All right, hello, and welcome to CS867 QIC890 class 4. This is week 4. So I've already posted the notes. Today we're going to cover the polynomial method. So this is a way of proving that quantum algorithms don't exist, so a way of proving quantum lower bounds in query complexity. It has an analog as well in communication complexity. So this is kind of kind of an interesting method in that it relates the theory of quantum computing into the theory of polynomials, and there's a sort of a separate but related theory of approximating functions using polynomials, and this field of computer science, or this field of mathematics, is closely related to quantum computing, which is interesting and perhaps surprising. So so to start, we will start with the following observation. So basically, the claim will be that, well, our basic claim is that a quantum query algorithm gives rise to a polynomial. So suppose we have a quantum query algorithm Q, and Q is a tuple here of unitaries, right? So this is a quantum query algorithm in general. It looks like this tuple of T unitaries. So this quantum algorithm Q is making queries to a string X, and the string X is an n-bit string. And so the very basic observation, or the key insight of how to use polynomials to low-bound quantum algorithms, is that the acceptance probability of Q and X, so this is the probability that Q of X, outputs 1, or in other words, that the algorithm accepts X, where here this probability is a polynomial. In the bits of X. So this is the key insight. And so recall that here we use the notation Q of X to denote the random variable of what Q outputs when it's run on the string X. So the probability that Q of X is 1 is just a probability. It's a number between 0 and 1. But of course, this number depends on X, right? So here we're thinking of having a fixed algorithm Q and plugging in different strings X. And the observation here is that the acceptance probability that Q has when you plug in X is a polynomial in the bits of X, and its properties, this polynomial inherits properties of the quantum algorithm. So if your quantum algorithm, in particular, if your quantum algorithm is one that uses few queries, if T over there, if T over here is small, then the degree of the polynomial is small. So in particular, it's a polynomial in the bits of X, and then of degree at most 2T. Okay, so if T is small, then the degree of the polynomial is small. And so we will go through why that is, but maybe we should start by noting that it's kind of weird to define a polynomial in the bits of x in the first place. What do we mean exactly by a polynomial in the bits of x? So the first thing to note is that what we mean here is, well, we mean, you know, an n-variate polynomial, not a single variate polynomial, but we have n variables. So the polynomial might look like x1, x2 plus x1, x3 minus 3.2 x7. Okay, so this is just an example polynomial. And here x1 and x2 and so on are the bits of the string x. Okay, so they're variables that are representing the bits of the string x. And another thing to note is that when we say polynomial, we mean real polynomials. So the coefficients here are going to be real numbers. The field of the polynomials is the reals, basically. So the coefficients will be real. And you know, maybe another point of confusion, another thing to notice here that's kind of weird, is that normally we think of the input x. What is the input x here? It's just a string. It has the characters in that string. You know, we write them as 0 or 1, but they're actually arbitrary, right? They could be a and b. Like this, we could say, okay, instead of x in 0, 1, we can say x is in, you know, the set of these two characters, triangle and square. Okay, so, you know, if x is in this set, then of course, well, it wouldn't make sense to talk about the polynomial degree or any polynomial in the bits of x, because the bits of x here are not 0, 1 valued, they are triangle square valued. So given that, you know, that there's sort of no meaning to the bits, why would we want to ever take a polynomial in the bits where we're actually interpreting the bits as the numbers 0 and 1? Why would we ever want to do this? And you know, part of the answer is that you know, so long as we only care about the degree of the polynomial, then it turns out it's not going to matter if we represent the characters of the string by 0, 1 or by you know, 1 and minus 1, or flip it so that you represent them by 1 and 0 instead of 0 and 1, the two characters, if you exchange the bits 0 and 1 with each other, or you know, 5 and 6, or really anything else. It's not going to affect the degree of the polynomial. So you can get different polynomial representations of a function depending on kind of what you choose for your alphabet symbols. But so long as you choose sort of two different real numbers, you'll get the same degree, like you'll get sort of the same expressive power per degree of your polynomial. So, so you know, the sort of the reason why we would talk about polynomials in these in the 0 and 1 characters is that the choice of 0 and 1 here is arbitrary, and we could have chosen any other two real numbers. And a common choice is 1 and minus 1 instead of 0 and 1. So that's another common choice. And maybe yet another point of confusion or another point of weirdness here with this definition is that when xi, all these variables like x1 here, if we know it's either 0 or 1, then of course x1 squared equals x1. So we kind of say polynomial, but you would never want powers higher than 1. So why are we even talking about the degree of a polynomial? And it turns out that yeah, that it's true, we never want powers higher than 1, but we can multiply different variables together. So we can, you know, write a monomial like this. And this monomial is going to have degree 3. So we're going to call this degree 3, even though each individual variable is only degree 1. And of course, some of the variables here are degree 0. So for example, there's no x3. It has it was not included in this monomial, so it doesn't contribute to its degree. If we add it here, then of course the total degree of this polynomial is still 3. Okay, so you know, these are the types of polynomials we're going to be dealing with. These are n-variate real polynomials that are, well, they're called multilinear in that they don't have any powers larger than 1 for the individual variables. So it's n-variate, real coefficients, and multilinear. And these polynomials are going to basically represent the acceptance probability of a quantum algorithm. Well, maybe we should start by seeing why that is before we study them further. Okay, so let's show why we get a polynomial out of a quantum algorithm. So let's say that we have a quantum algorithm Q, okay, and it has it makes T queries, right? So okay, so it's this tuple of T plus 1 unitaries. Okay, so let's consider the state of the quantum algorithm when it's run on X. Okay, so at the beginning, of course, we start with we start with psi init. Okay, but then what do we do to it? We are going to I guess we'll apply U0 and then apply UX, right, and then apply U1 and so on. So we're going to apply all these unitaries. So let's denote by psi0 the state right after applying the unitary U0. Okay, and then similarly, psi1 is going to be the state right after applying U1. And then, in general, we're going to define all of these up until the last one. Okay, so we have all these intermediate states that we get when we run Q on X. Now, the first one does not depend on X, but all the rest do, right? So psi1 and psi2, they all have a dependence on this UX there. And therefore they change when you change X there. So this is sort of the transcript of a quantum algorithm, kind of what it does as it goes along. And now each one of these is a unit vector, right? Because it's a quantum state. So it's a vector. We can look at its coefficients. So we don't know how long this vector is. It might be very long. It depends on the kind of the dimension of the workspace, which we kind of allow it to be an unbounded register. We usually take it to be finite, so it's an unbounded. We don't care about the size though. So we don't really know the dimension of these vectors, but they're all the same dimension. And what we do know though is that the first one has no dependence on X. So the first one is sort of a vector of constants for us, right? So the first one, just look like 1 sorry, I mean, I guess I should normalize. So maybe the first one looks like some units vector, like 1 and 3 and -2, such that the total, the total 2 norm there is 1. So it's a unit vector. Okay, but it's all constants in there. In theory, they could be complex. So these you can have an I here, or an I plus 1. We can have complex entries. Okay, so that's fine. So that's size 0. So what happens when we apply UX? Okay, so now I kind of want to apply well, we know that UX maps. What does UX do? UX takes I and B. So let's write this in phase. So UX takes I and B to -1 to XIB. So this is a phase query. Okay. And okay, so this is a phase query. I'm going to maybe do a little bit of a sleight of hand here. So let's just, well, actually, okay, maybe a simpler way to view it. We'll split this into two cases. So we know that we're mapping this I0 to just I0, right? And we're mapping I1. We're mapping I1 to -1 to the xi I1. Okay, but -1 to the xi, this is equal to -1 when xi is 1, and it's equal to 0, sorry, to 1 when xi is 0. So it's actually 1 minus 2 xi. Okay. Okay, so what happened here is that we have this long vector, this size 0, and we can look at one amplitude, one entry alpha. And what UX does to this entry is that either it maps it, this alpha, either becomes alpha in the case that this entry corresponds to a basis state that looks like this, or else it becomes 1 minus 2 xi alpha. Okay, so we sort of, each amplitude here either gets left unchanged or gets multiplied by 1 minus 2 xi for some I. Okay, and that depends on the basis states that correspond to these entries of the vector. Okay, but for every entry, it either gets multiplied by 1, basically does not get changed, or it gets multiplied by a term like this. Okay, that's what UX does. That's the transformation of UX, and the transformation of one of those little UT matrices. Well, these have no dependence on X, and they're linear transformations. So you can think of that when we apply that to some vector. We apply that to some vector. We're only reshuffling the vector, sort of. We're taking linear combinations. Like if we had alpha, beta, gamma here, then we might have alpha plus beta and like gamma minus 2 alpha, and we will have linear combinations, but no dependence on X gets introduced. Okay, so if you think about it, what happens here is that the entries in the vector for size 0, they are degree 0. They're each degree 0 polynomials in the xi variables. Okay, so here we have degree 0 for psi 0. And then each entry in the vector of psi 1 is degree 1. The degree is 1 there. Because they got multiplied by terms like this to increase the degree 1. I should say the degree is at most 1, I guess. Okay, and as we go down, we can sort of get by induction that even the last one will have degree at most t. Okay, now these polynomials will have complex coefficients because all these the UT unitaries, they can have complex entries. So in general, these are going to be polynomials of degree at most t with complex coefficients. But basically, well, we're not yet done. So we now want to talk about the acceptance probability. So we want to get this expression. Okay, we want some expression for this term, right? For this probability. And this probability is what we get when we measure some register of psi t. Remember, these psi t's, they have dependence on X. I should probably like put an X exponent or something, because other than the first one, they have dependence on X. Okay, so we're going to measure psi t, or just let's say the first qubit of psi t, and see what we get. Okay, what does that correspond to in terms of the vector? What that corresponds to is basically we're basically going to take some of this norm squared of alpha for some alpha. Those that correspond to the algorithm outputting 1. For some alpha, so some entries alpha in psi t, right? So within the vector psi t, some of the entries, we take their norm squared and we sum them up. And that's going to be a probability of accept, okay? Those entries that correspond to some specific coordinates. Okay, so that's the acceptance probability. Now this norm of alpha squared, we can write that as well, this norm of alpha squared, this is basically the real part of alpha squared plus the imaginary. Okay, so if we take this entry alpha and we split it into a real part and an imaginary part and we square them, and we sum their squares, we get the modulus squared of alpha here. So we just need to sum all that up. Now, remember, we are in this vector psi t of x. So all these alphas, the alpha here is a complex polynomial in these n variables, the xi variables. So we have here that alpha is already a complex polynomial. So if alpha looks like whatever x1, x2 plus 1 plus I x3 or whatever, we can take sort of the real part of alpha and the complex part of alpha, and those will just be polynomials, right? So so if we want to write alpha as alpha real plus I times alpha the imaginary part, then alpha real and alpha imaginary will be real polynomials with real coefficients. Okay, and so here we get a sum of squares of real polynomials, and each of these polynomials is of degree at most t. So the sum of squares of real polynomials of degree at most t, well, when we square the polynomial, we can increase the degree by a factor of 2. So in each term of the sum has degree at most 2t, and so the final polynomial, which we get by expanding out all the sum, is degree at most 2t. Okay, so we get a polynomial expression for exactly the probability we wanted for this probability here, and the polynomial we had has degree at most 2t. So this is sort of the main insight here, and it's a very useful insight for understanding quantum algorithms, and especially for proving quantum lower bounds. Okay, so so basically quantum alg implies, okay, and then if we had t queries here, then it has degree at most 2t. Okay, so or I should say at most 2 queries implies degree at most 2t. Okay, not every polynomial converts back into a quantum algorithm with the same acceptance probability, right? So that's the backwards conversion doesn't necessarily work. Okay. All right. So let's keep going here. So if we think of the polynomial p of x that we get from a quantum algorithm q, so if we took q and we converted it to p of x, we notice that p of x has a few properties. Okay, so one is that p of x is in the range 0, 1, regardless of the input. Okay, so that's because P of X represents an acceptance probability of the quantum algorithm. So in particular, a probability. Okay, so P of X will always be in the range 0, 1. Another property of this polynomial P of X is, well, depends on the action of Q, but suppose if Q computes F to error epsilon. So suppose Q computes F to error epsilon. What does that mean? That means that the probability that Q of X does not equal F of X is less than epsilon. Okay. If this happens, then we know that, if F of X is 1, then the probability that Q of X equals 1 is at least 1 minus epsilon, right? And if F of X equals 0, then the probability that Q of X equals 1 is at most epsilon. So what we get here is that for the polynomial, because the P of X is this probability that Q of X is 1, then we get that P of X is within epsilon of F of X. Okay, so if Q computes F to error epsilon, then P of X minus F of X is at most epsilon in absolute value. So P of X is always within epsilon of F of X. Okay, and also P of X cannot exit the range 0, 1. Okay, so and this is going to be for all X in the domain of F. So here, this works even if F is a partial function. If F is a partial function, then the guarantee that Q computes F to error epsilon only gives us a constraint on the X's in the domain of F, and we are unconstrained outside the domain of F. But P of X still has to be bounded in 0, 1, even outside the domain. And the reason is that even if you plug in a bad input, an illegal input to the quantum algorithm, even then the quantum algorithm will accept with some probability. It will have some probability of outputting 1. That probability will be between 0 and 1, and P of X is that probability for that X. So P of X is always going to be between 0 and 1 for all strings in the Boolean hypercube. Regardless of what the quantum algorithm does, if the quantum algorithm computes F, where F is a promise problem, a partial function, then we have this guarantee as well. Okay. So a useful definition we didn't make in the notes is that we say that P approximates F to error epsilon if these conditions hold. So this definition is a definition about P that doesn't mention the quantum algorithm Q anymore. So now we can talk about just arbitrary polynomials and variate polynomials and ask whether they approximate F or not to error epsilon. And we say that approximate F if both of these conditions hold. So basically the polynomial needs to be bounded in 0, 1, and it needs to be within epsilon of F. Okay. And so we can make a definition. We can define a measure, a complexity measure F. We can define deg epsilon of F, or sometimes with a tilde above it. This is the approximate degree of F to error epsilon. This is going to be defined as the minimum degree of a polynomial P, which approximates F to error epsilon. Okay, so this is the minimum degree of any polynomial which satisfies these conditions. Okay, and so and this is called the approximate degree of the polynomial sorry, of the function f. Okay. So one thing we immediately get is that, well, if we think about this measure, what is one way to get a polynomial which approximates f to error epsilon? It's to start with a quantum algorithm. And so if you start with a quantum algorithm, the degree of the resulting polynomial will be at most twice the number of queries. So we get this. We get that the approximate degree of f is at most twice the quantum query complexity of f to the same error level. Okay, that's because you can take any quantum query algorithm and convert it into a polynomial approximating the function of at most twice the degree. Okay, so we can of course write that as q epsilon of f is at most a half deg epsilon of f. Okay, and this just tells us that one way of lower bounding q of f, one way of showing that this is big is to show that the right hand side is big. Okay, is to lower bound the approximate degree of f. Okay, now I should also note that when epsilon we omit epsilon when epsilon equals 1/3. This is because we don't really care about constant factors usually. So we can write this. Okay, so note that the quantum query complexity is the same for any error, for any constant error level because of amplification. It turns out that approximate degree can also be amplified. So if you have a polynomial which approximates a function to error 1/3, and you want it to approximate the function to error 1/10, it's actually possible to convert this polynomial to have lower error by amplifying, composing it with a different polynomial essentially, which increases the degree, but only by a constant factor. So you can choose, the epsilon, you can convert from one epsilon to another and only pay a constant factor, assuming epsilon is constant. Okay, so we get this useful bound here. And so the next question, I guess, is that, you can say, okay, that's great, but how are we going to lower bound this approximate degree of f? How do we lower bound the right-hand side? So it's maybe more concretely, we can start with some functions. We can start with parity, say. And we can say, how do we lower bound the approximate degree of parity on n bits? Okay. This is, it seems like a bit of a mess because I can try to express parity, by writing some polynomial like this, and how are you going to figure out if I'm right or not? Like, is this the parity function on 3 bits? Who knows? I mean, you have to start plugging things in, right? And how do you know if that there is no polynomial approximating parity, even with some error? Okay, so to show that you must use high degree sounds like it's a complicated task. There's this trick to doing so, and the trick dates back to the 60s. It's from like this book by Minsky and Papert. So it's this trick of symmetrization. We have here an n-variate polynomial. N-variate polynomials are very difficult to understand and get a handle on. So what we're going to do is basically convert it to a single variate polynomial that has some similar properties. Okay. So basically, suppose you have p. Okay, so we have some polynomial p of x, and it's an n-variate polynomial, right? So we can think of it as taking as input n different variables like this. Okay. So we have this polynomial p. Now we know that parity is a symmetric function, right? So suppose p approximates parity. We would like to say, okay, therefore p has to be symmetric, has to be invariant under shuffling these bits. Of course, we don't have a guarantee of that, right? Maybe this particular polynomial approximating parity is not symmetric, but we can kind of force it to be symmetric. So we can define a polynomial. Okay, so let's define a polynomial p p hat. Okay, and p hat is going to be the average of p of every possible shuffling of the input. So we're going to shuffle the input bits at random, apply p to that, and just take the average of what we get. So what this ends up being is 1 over n factorial sum over sigma in Sn. So this is here sigma is a permutation, and Sn is the set of all permutations on n elements, of p of x sigma. Okay, where x sigma is the string that we permuted by sigma. So x sigma is a string, and at position I, it's equal to x sigma of I, where sigma is as a permutation. So sigma of I is another index j. This notation might seem complicated, but all that's going on here is that x sub sigma is a shuffling of these bits according to the permutation sigma. So it's just one particular way to shuffle these bits around, okay, to permute them. We are summing over all the ways of permuting them, and for each permutation, we are plugging that into p. Okay, so we're summing that over all possible permutations, and then we're dividing by the number of permutations. There's n factorial permutations, so we're dividing by n factorial, and so we get basically the average value of p applied to any permutation of the input. Okay, and that is a polynomial p hat. And note, so first, one thing to note is that if the degree, let's say that the degree of p is d. So here, every term in the sum also has degree d in the original variables, right? So this polynomial on permuted input is still degree d. We're summing things that doesn't increase the degree, and dividing by a constant doesn't change the degree. So we get that the degree of p hat is also at most d. So it's at most the degree of p. Okay, so we get this new polynomial. It's basically going to have the same degree. Maybe we got lucky and it even decreased. Okay, but generally it's just going to have the same degree as the original polynomial p. But now it's symmetric, and it's symmetric in the sense that now if I permute these inputs in any way I want, then I'm going to get the same answer. So if I permute the bits, then you can see, because here I'm applying every possible permutation and summing it up, then it doesn't matter what the order of the original bits was. It doesn't affect the final answer. So the upshot of all of this is that p hat is now a symmetric polynomial. It has the same degree, or maybe smaller if we got lucky, as the original polynomial. And also because the original polynomial approximated parity. So if p approximates parity, then p of any permutation should also approximate parity. So p of x sigma should also approximate parity, because the parity of x and the parity of x sub sigma are the same. Parity doesn't change when you shuffle the bits. So because of this symmetric property of parity, we get that if p approximated parity, then each of these p of x sub sigma still approximates parity of x. So each of these terms still approximates parity of x. And now we're taking an average of n factorial many things that approximate parity of x. So that still approximates parity of x. So what we get here is that p hat also approximates parity, okay? And it has the same degree or small degree than the original p, and it's symmetric. So what we've done is basically we've converted p, even if p wasn't symmetric originally, we forced it to be symmetric. P hat is now going to be symmetric, and it's going to have the same properties in every other way, as far as we care about. So we basically forced this polynomial approximating parity to be symmetric. Okay. So this is, you know, one, the first step is to kind of say, if we had any polynomial computing parity, no matter, you know, to some fixed area epsilon with fixed degree d, if we had that, then we can convert it into a polynomial that is symmetric and approximates parity. So we can assume without loss of generality that our polynomial approximating parity is symmetric. Okay, so this was the first step. The second step is to note that a symmetric polynomial, so if we can think of kind of p hat of x, because it's symmetric, and it's also multilinear, because remember that you know, xi squared equals xi, so we never need, and that's also xi cubed. We never need powers that are higher than 1 in xi. So the polynomial is also multilinear. So we can write this polynomial as basically some term of degree 0, some constant term, you know, like let's say a constant term c, plus, let's say it's called c0, plus c1 times all the terms of degree 1. So all the terms of degree 1 have to occur with the same coefficient here, because the polynomial is symmetric. So all the terms of degree 1 have to occur with the same coefficient c1. Okay, so these are all the terms of degree 1 here. And then we can write down all the terms of degree 2. And they all have the same coefficient c2. They look like this: x1, x2 plus x1, x3 plus dot, dot, dot. You know, and you actually have n choose 2 of them here, xn minus 1, xn. But you know, you're actually going to have n choose 2 different terms here. Okay, and so on. So we can write up the polynomial like this. Okay, up to cd, where d is the degree of p hat, or the original degree of p, I suppose. So you know, after cd times something, when you're going to have like n choose d terms there within that that we're summing over, and n choose d monomials there. So we can write it like this, and if we let you know, if we just let t be this sum, then what we notice is that that t squared, what is t squared? T squared is basically, well, we get all the squares, and then we get all the squares, and then we get this term here in terms of C2. So we get all the pairwise products. Okay, but the squares simplify because we know these are either 0 or 1. So this simplifies to t plus the sum of plus all that, the sum of the pairs, the pairwise product. So we can get that the sum of the pairwise products this sum of pairwise products is actually equals to t squared minus t. Okay, where t was over here, t was the sum of the variables. Okay, so t is basically the Hamming weight of the string here, and we get that p hat of x is equal to c0 plus c1t. T has some dependence on x here, so t is the Hamming weight of the string x, plus c2 t squared minus t plus. And it turns out that you can write the kind of triple-wise products, the sum of all the triple-wise products, you can write that as a polynomial of degree 3 in t. So you can sort of do a similar trick, do t cubed and kind of expand that out. And you can write some polynomial here, you know, plus or minus like the t squared terms and the t term I don't remember what the coefficients here are, maybe 2 and a 1 or something. But anyway, so you can write down C3 times some polynomial in T, okay? And you can keep going doing this until you get to CD, and it will be some T to the D, some polynomial of degree D in T, okay? And so what we get is that basically P hat of X looks like Q of T, okay, where T has some dependence on X. So maybe we should write Q of T of X, where T of X is I'm just putting of X to highlight that it has a dependence on X. So we can write P, so let's ignore this one, and we can say that P hat of X is Q of T of X, okay? But Q here is single variate. Okay, so Q is just a single variate polynomial. Okay, and also we have that the degree of Q is at most D, which is at most the degree of P or P hat. Okay, so we've basically gotten this polynomial P hat to be, we basically wrote P hat of X is equal to a single variate polynomial of the sum of all the variables. Okay, so we have, we started with an arbitrary n-variate polynomial P, but because it approximated a symmetric function, we've kind of reduced it into this P hat, which was symmetric, and that turned out to be a single variate polynomial Q of just the sum of all the variables. Okay, so that's very convenient. We've simplified the structure of this polynomial a lot. It's now just a single variate polynomial of degree at most D applied to the sum of all the variables, or the Hamming weight of the string. Okay, and if we think of, you know, what does Q do? So we know that Q of 0, right, is equal to Q of 0 plus 0 plus, right, which is equal to P hat of right, which is approximately equal to parity. Oh, of course, P hat approximates parity. So it's approximately the parity of the 0 string, which is 0. Okay, so we know that, you know, Q of 0 has to be in this range between 0 and epsilon. Okay. What about Q of 1? Well, Q of 1 looks like this. We just have a 1 there, which is P hat of this string, you know, basically the string E1, the string that looks like 1, 0, 0, 0, which is approximately equal to 1 because parity of the string is 1. So this is Q1 is in 1 minus epsilon and 1, because P hat has to output something that's within epsilon of the parity function applied to the string. And it also has to output something between 0 and 1. So it's got to be between 1 minus epsilon and 1. And Q2, well, Q2 is P hat of 1, 1, 0, 0, 0, 0. And we know the parity of the string is 0. So this is in 0 epsilon again. Okay, so what we get basically is, you know, if we so we get bounds like this until Qn. Qn is P hat of 1, 1, 1, 1, 1. And that is, well, that depends on whether n is even or odd. So we get either it's in the range 0 epsilon or in the range 1 minus epsilon 1, depending on you know, the parity of n. So on whether n is even. Okay, so let's just plot this graphically. So if we just plot the graph of Q, here we have these X and Y axes. And let's say this is 0 here, and this is 1 over here. Okay. So we know that Q starts somewhere between 0 and epsilon here. It's somewhere in this range, so it has some dot here. And then at 1, it's between 1 minus epsilon and 1. So it's this is, let's put here, here's 1 minus epsilon. So the value of Q, like a Q of t, the single variate polynomial, if we plot it, it's going to go something like this. It's going to pass through some point here that's between 1 minus epsilon and 1 at the value 1, right? And then at the value 2, when we plug in 2, it's going to go somewhere in this range, some point between 0 and epsilon. Okay, and then it's going to pass at 3 between 1 minus epsilon and 1. Okay, and then this is going to go until n. So it's going to go like this. Okay, and then it can do whatever it wants outside this range. Outside this range, we have no idea what it's going to do. So it's some single variate polynomial that looks like this. Okay, and so if you look at what the degree of Q, what is the degree of a polynomial that looks like this? Well, you can see that Q has to reach, kind of change directions, go up and down between maximum and minimum a lot, right? So actually, you know, if you think of how many times Q crosses a half here, okay, so if you look at Q of t minus a half, then at 0, then this is less than 0, it's negative. We're below that half bound because we're between 0 and epsilon. And at 1, we're above, and at 2, we're below, and so on. So we have to cross this line at least n times, at least once in between each of these ranges. From 0 to 1, we have to cross the line once. From 1 to 2, we have to cross it once. From 2 to 3, and so on. So we have to cross the line n times. Okay, so this means that Q of t minus a half equals 0 happens n times. So it has n solutions for t in the range 0, n. Okay. Okay, so this polynomial Q of t minus a half has n zeros. If it has n zeros, then its degree has to be at least n. So we actually have that deg Q is at least n. Okay, but we also know that deg Q is at most deg P. Okay, and it turns out the degree of any approximating polynomial is at most n. You know, one way to see that is just to know that there's always a quantum algorithm computing a function that has degree at most n. But it turns out we can exactly express any function you want using degree at most n, any Boolean function. So any function defined on the Boolean hypercube, you can represent it exactly. You know, with the polynomial of degree at most n. Okay, so what we know here is that actually deg Q equals n. Okay, so we've concluded basically that that deg P is also equals n. So if we have polynomial, the best polynomial approximating parity to any error epsilon less than a half must have degree n. Or in other words, we conclude that the approximate degree of parity equals n. And this is actually for any epsilon less than a half. Okay. What does this mean? So this means that the quantum query complexity of parity is at least n over 2. Okay. You know, also for any epsilon less than a half. Okay, so a quantum algorithm cannot compute parity better than faster than n/2 queries, even if we allowed a lot of error. Can we achieve n/2? Well, when n is even, then yes, we can achieve n/2, and we can do it by basically using the Deutsch-Jones algorithm to basically get the parity of 2 bits with a single query. And we can do that n/2 times, and we get, n/2 different parities of 2 bits, and then we can do the parity of all of our results, and we'll get the parity of all the strings. So we can actually achieve this. So n/2 is tight. So in fact, this holds. Of parity on n bits is exactly n/2 when n is even. And I guess it's n+1/2 or something when n is odd. This is for all epsilon less than half. Okay, so it's actually the same regardless of the value of epsilon. Okay, so this is sort of the main idea behind the polynomial method. So I would like to just expand a bit more in 2 directions. So one direction is, for whether we can do a slightly more complicated symmetrization arguments. So basically, can we do the symmetrization argument for functions that are more complicated than parity? A function that's extremely useful to lower bound is this PromiseOR function. PromiseOR on n bits. So this is a function that is 0 if x is all 0 strings, and 1 if Hamming weight. If the Hamming weight of x is 1, and it's star otherwise. So basically, we promise that the Hamming weight will either be 0 or 1. Okay, so it will never be something else. So this is the PromiseOR function on n bits. So effectively, this is a function that can be solved with Grover search. So we know basically that Q of PromiseOR is equal to at most root n up to constant factors depending on the exact implementation of Grover's algorithm. So we would like to prove a lower bound on this. And because PromiseOR is a symmetric function, we can say that if P approximates PromiseOR, okay, then we can write the symmetrization P hat also does. This is the symmetrization that we defined before. And then we can say, and P hat of x can be written Q of where here Q is a single variate polynomial, and the degree of Q is at most the degree of P. Okay, so we can assume basically without loss of generality that if we have a polynomial that approximates PromiseOR, then the polynomial might as well look like a single variate polynomial applied to this sum, to the Hamming weight. And then what we know about Q, so what do we know about Q this time? We know that Q of 0 to the 0, right? Q of 0 is equal to P hat of 0 to the n, which has to be well, it's the PromiseOR applies to 0 to the n roughly, so it's between 0 and epsilon. And we know that Q of 1 is p hat of 1 which is between 1 minus epsilon and 1. Okay, but what we know about q of 2 and q of 3 and so on, well, those are equal to p hat of x for some other x outside of the promise. Okay, so those are equal to, p hat of some x outside the promise. All we know about that is that it's between 0 and 1. Okay, so we know that these values are all between 0 and 1. Okay, so if we plot the graph of q again, so if we plot here, okay, so let's put epsilon here, 1 minus epsilon, and 1. So we know that we're going to be over here between 0 and epsilon at the beginning. Then we'll be between 1 minus epsilon and 1 at 1. Okay, so we'll do this. Okay, and then for the rest, we just know that we'll be somewhere between this range here. So at the value 2, we'll be somewhere between 0 and 1. At the value 3 will be somewhere between 0 and 1 after the value n. So we know that we pass through some points here. So we do this. We don't know for sure that we won't spike up and go back down. Maybe that will happen. Okay, we'll do something like this. And of course, outside of the range, we can do whatever we like. Okay, so the polynomial q, this is a plot of q of t in the single variable t. It has to look something like this. Okay, so it has to be bounded between 0 and 1 on n different points, n plus 1 different points, I guess, on all these integer points. It's bounded between 0 and 1. It doesn't go too crazy. Moreover, it kind of jumps sharply. At the value 0, it's between 0 and epsilon. At the value 1, it's between 1 and epsilon and 1. So it jumps sharply here. And then it kind of stays reasonably bounded. Okay, so it turns out that there is a theorem that tells us that polynomials have a hard time doing this unless they have high degree. So in particular, suppose you have a polynomial that's bounded in a rectangle. Okay, suppose you have a polynomial that stays within this rectangle. Well, one polynomial that stays within a rectangle is just a constant polynomial, right? Like we can have q of t equals a half. This is a polynomial that stays within the rectangle, but its degree is 0. Okay, so this is always possible. A polynomial can always stay within a rectangle by just having, for example, degree 0, or we can even do this 1 plus a half plus 0.00001 times t. We have such a small coefficient on t that we don't even notice that this line is moving, so it will stay within the box. So polynomials can stay within the box so long as their coefficients on these higher terms are small. So now Markov brothers inequality actually talks about the situation where we have a rectangle and we have a polynomial that stays within the rectangle, but we know that its derivative is large. So the polynomial does move quickly, at least at some point. So the polynomial at some point here moves quickly. It has a slope like this, okay? And then, except for that, it stays bounded within the rectangle. But here it has a high slope, okay? And if the length of this is n, and the length of this is 1, which is sort of our situation here, and we know that this is what the polynomial doing is it has a high slope here, then the degree of the polynomial, the degree of q, I guess, the degree of q. So Markov's inequality says that the degree of q will be at most, the slope at this point, the slope here, let's call it m. So it will be at most m times root n, where m is the slope here. Okay, so this is basically q prime of z is equal to m for some z within this range, within the box. So if within the box is achieves slope m, then the degree is at least m times root n. Okay, so this is called Markov brothers inequality. because there's a different thing called Markov's inequality. So this was actually proven by Markov's brother, the brother of the other Markov for Markov's inequality. Anyway, so this polynomial that we have here, it's almost this situation, okay, except that it's not bounded in the box. It's only kind of bounded on integer points. Okay, but there's a simple proof that says that because of Markov's inequality, even if the polynomial is bounded by, if the polynomial is bounded on integer points, it's sort of good enough. Why? Because, you know, if it escapes the box here, suppose it managed to escape the box like I drew here, well, then it just contained in a somewhat larger box. Okay, so it contained in a somewhat larger box. And then we can scale this down. We can divide it Q by something to make it contained in a box like this. And note that in order to escape the original box, basically in order to escape the original boundaries here, it needed to have very high slope. Like if you look at the slope here that I drew, it would have very high slope. So if it wanted to escape, it must have high slope. And so even if we scale it down, it will have slope that's at least a constant, slope that's at least a half or something. So because of this, you know, the polynomial doesn't, so even if the polynomial escapes the bounds, then it's going to have, Markov's brother can apply. If it doesn't escape the bounds, then we know that because this polynomial Q moved from roughly epsilon or less than epsilon to more than 1 minus epsilon, it has slope somewhere in here. It has slope that's at least 1 minus 2 epsilon. Okay, so, oh, and I think I got this wrong. I think this was supposed to be a root of mn like this. Okay, I think I got this wrong. So in the notes, I have a correct version of Markov brothers inequality. I think this is supposed to be a root m times root n. Okay, so then what we conclude here is because of this modified version of Markov's brothers inequality, and the formal proof is in the notes, we get that the degree of Q is at least square root of 1 minus 2 epsilon times n divided by some constant. I don't really remember what it was, maybe 2 or 3 or something, that we lose by basically the fact that the polynomial is only bounded on integer points. We lose some constant factor there because of that. And because this is, you know, the degree of Q is the most degree of P, we get that the degree of any polynomial approximating PromiseOR is at least omega root n. So we get this. We got the degree of PromiseOR in n bits is equal to omega root n. Okay, and then of course Q of PromiseOR is only larger. Well, it's larger than half this, I suppose. So so we have an omega root n lower bounds. So of course we have the upper bound of root n from Grover search. So this is saying that the lower bound also holds. So Grover search is tight for this PromiseOR function. Okay. So this is a very nice argument that comes up a bunch. There's a similar argument in the notes for the majority function. The majority function actually requires something called Bernstein's inequality, which can be, Parity showed can also work when you're only bounded on integer points. And it's basically saying that, oh, Markov's inequality gives you can improve this to a better bound if the point at which the slope is high, you know how we have a high slope here somewhere. If the point at which the slope is high is in the middle, is near the middle of the box, then your lower bound on the degree is going to be even better, even larger. Okay, so if you have a large slope somewhere in the middle here, to achieve, and so in other words, if a polynomial stays in a box and has large degree in the middle of the box, so it does this, then its degree needs to be very high. Okay, so in particular, if the slope in there is like omega 1, if the slope in there is roughly 1, then the degree of a polynomial which stays in the box and has slope 1 in the middle, then the degree of such a polynomial is omega n. Okay, whereas if the slope of omega 1 was near the boundary of the box, okay, so if the slope, if the slope of omega 1 was near the boundary of the box, and over here you had omega 1 slope, then the degree of the polynomial would be only omega root n. Okay, so polynomials that stay bounded in a box and sort of have non-trivial movement, they can do that with degree root n, where n is the length of the box divided by the height, I guess. If the large movement is near the boundary of the box, because then you can sort of escape afterwards like this. Okay, so, but if you need to stay bounded the whole time and you have high movement here, so you need to basically keep moving up and down in order to be contained within the box. That means you sort of need to have a lot of zeros, a lot of minimum and maximums and whatever. So you need high degree in order to do this. Okay, so that's sort of the rough intuition behind these theorems, Bernstein's theorem and Markov brothers inequality, I guess. Okay, anyway, the notes have the details. Using this, you can basically show that the approximate degree of majority on n bits is omega n. Okay, which means also the quantum queer complexity is omega n. Okay, so you don't get any speed up for majority. You have to, up to a constant factor, read all the bits, even with a quantum algorithm. Okay, so that's almost all the content that I wanted to cover in this video. So just one final note is that a technique that you'll see in papers, a kind of more modern way of lower bounding polynomial degree, is it's moved away from symmetrization arguments a little bit, because people want to lower bound non-symmetric functions as well, the polynomial degree of non-symmetric functions. And so they do this by writing polynomial degree as a linear program and taking the dual. And it kind of becomes this lower bound technique. There's a theorem in the notes, I guess, that says that if you have a function f, then to lower bound, if you wanted to prove that this is bigger than something, then you only need to show, you need to provide sort of two objects. One is you need to provide a distribution mu. This is a distribution over the Boolean hypercube, and you need to provide a modified function f prime, which is basically, think of it as kind of a modified version of f. It's almost f, but not quite. So it's just a modified version of f, such that, so you want to provide these two things, such that f and f prime mostly agree on inputs from u. Okay, so basically, if you sample the inputs from u, you'll find that with high probability f and f prime agree. Okay, how much does it need to agree? That depends on epsilon. So something like 1 minus epsilon-ish or something like that. So f and f prime have to mostly agree on inputs from u, and f prime has zero correlation with all low degree monomials. Against mu. So basically, if you take any monomial of degree at most t and you look at its correlation with f prime, so you just sample from u and kind of check if f prime and the monomial agree on the input or not, then they'll agree half the time and disagree half the time. It will just be totally random. on input from mu. So on when you sample from mu, then it looks like there's no agreement at all. There's no correlation between f prime and any monomial that you pick, any low degree monomial. Okay, so f prime is kind of cannot be approximated by low degree monomials, or and basically this implies even by polynomials in a very strong way. So if you have, you know, mu and f prime with these conditions, then it would imply that the approximate degree of f is large. And it turns out that this is a complete lower bound technique in that whenever the degree of f really is large, you can prove it using this method. So this method is always tight. It's always in theory possible to find mu and f prime to get this lower bound to work, to get the correct lower bound to work. Okay, so this is another way to, you can even define approximate degree this way. Okay, so because it's going to be exactly tight for approximate degree. Okay, so the notes have a few other things that I didn't mention in this video. Not too many, mostly, let's see. So the notes mention how you generalize polynomials to non-Boolean inputs and non-Boolean outputs. The notes talk a bit about polynomials that act in the kind of plus one minus one basis. So this is here, the polynomial expects input in +1 -1 instead of in 0 1. You know, such polynomials can easily be converted back and forth from polynomials that expect inputs in 0 1 to the end. So it's easy to convert back and forth just by modifying the polynomial without even changing its degree at all. So the notes talk a bit about that. The +1 -1 basis is often convenient in practice, so many papers use it. And of course, the notes go into more details on the proofs, you know, including how to prove the lower bound for majority. Okay, so that's all I have for this week. And on Monday, we will have the student presentations for 3 papers that, you know, that sort of all prove polynomial lower bounds in somewhat different ways and in somewhat different settings. All right, so I'll see you then.